I'm back here. Sorry, can you see and hear?
Yeah.
All right. Sorry about that.
Okay, so he's going to talk about projective and telescopic projection integrator for kinetic mixtures. So Rafael, please.
Thank you very much. Thank you so much for having me here. I'm sorry that I can't join you in person this week, but I will be there from next week. So hopefully there'll still be cake left for me. I'm counting on that. Today, I'm going to talk about a numerical project that I did during my previous postdoc in Lille. So all of this is work with Thomas Rey, and most of it was done in Lille. We finished the last details when I was already here in Oxford. So a quick outline of what we talk about today. I will first tell you about kinetic equations. I know that the audience here doesn't need much of an introduction, but I do like to start things from the beginning. And in particular, I will talk a little bit about what happens when we take a certain hydrodynamic limit in a particular scaling. And I'm talking about this because what I want to do is I want to capture the limiting behavior of the equation numerically with a scheme that will depend sensibly on this parameter. So the idea is to take your kinetic equation of choice, take the Knudsen number to 0, and hopefully have a numerical scheme which is asymptotic preserving in some sense. For this, we're going to use projective and telescopic projective integrations, which are somehow old ideas, which are having a new life recently, being used in kinetic equations. I will tell you a little bit about how the method works, why it works, how we calibrate it, and then I will show you the numerical examples and hopefully convince you that this is a sensible way to solve kinetic problems. So to start, I have to tell you what a kinetic equation is and what the Boltzmann equation is. I know most of you know it already, so I apologize if I'm boring you. We will talk in a very formal level today, so we don't necessarily have to get into the specifics. I'm considering a kinetic equation which has two main terms, a transport term and a collision term. F here is some distribution of particles. In some sense, we're talking about ideal gases here. And this equation really captures the two things that happen to the particles of this gas. The particles travel in straight lines, and every now and then two particles collide. And when they collide, there is some bookkeeping to do to see how the momentum and the energy is exchanged, to see basically how the velocity of these particles changes. So we have transport on the left, collision operator on the right, and we have this Knudsen number, this 1 over epsilon. This is defined as the mean length of the free path of the particles. So it's the average length of the path between collisions of these particles. And the intuition is a big Knudsen number means collisions are rare. So particles travel a long distance before they collide, whereas a small Knudsen number means the collisions happen very frequently. Somehow 1 over epsilon is the strength of the collision operator. So this controls the frequency of collisions. Now, we can define all sorts of momentum distribution. I don't necessarily care to go over every single thing. Just to say that I will write F in the number convention. So the integral of F in velocity and position gives me the number of particles, not the mass. This is so that we can define the model for a mixture a bit more easily. But if you're used to the density definition, then these two things are equivalent when the mass is 1. And if the mass is not 1, the moments are the same. You might pick up some constant in places. The point is that this distribution gives you everything you need to know about the gas. Tells you, for instance, the density of particles in terms of number of mass. It tells you the average momentum of the particles, the energy, the temperature. And in fact, I will be much more concerned with these moments than I will be with the distribution for reasons that will become clear in a moment. So this is my favorite video to describe kinetic equations. This is exactly what happens to the particles of a gas. Ignore the friction on the table. Two particles travel in straight lines, and before they collide, nothing happens. They simply travel at a constant speed, at a constant velocity. And when they collide, there is some exchange of momentum, some exchange of energy, but the momentum of both particles is conserved, and the kinetic energy of both particles is conserved. So we are assuming idealized elastic collisions. Now, at this stage, you might have a question, which is, why is he playing billiards with a ball that's not the white ball? And I don't have an answer for this. I apologize. Now, I have to tell you about the Boltzmann equation, and in particular, the Boltzmann collision operator. This defines the quintessential kinetic equation. And again, I'm not so concerned about the form of this collision operator today, but somehow everything we care about is encapsulated in this operator. This is the bookkeeping that I mentioned before. This tells you how you lose particles at some velocities and you gain particles at some other velocities because of this change of velocity that happens with the collisions. So again, the collisions are elastic. There's a nonlinear rate of collisions. And this operator does have really nice properties which we care about, somehow some macroscopic properties. First of all, conservation. Every collision between two particles conserves the mass because we're not modeling a chemical reaction here. So two particles come in, two particles come out. They conserve momentum and they conserve energy. And because these things are conserved at every collision, they must be conserved globally. So that's the intuition. And more importantly, there's an H theorem, right? Many people here again know about this, but it's worth stating it. Entropy always decreases unless you're a physicist, because they have a minus in front of it. We have a quantity, and this quantity, because we're considering an inhomogeneous kinetic equation, is not enough to just define the entropy integrated in velocity. This entropy satisfies a complementary PDE, but its integral in space is dissipated. And this boils down to this special property of the collision operator, which is that its integral against the logarithm is always non-positive. This dissipation really is at the heart of everything we do today, because this tells you really what this operator is doing, right? It's telling you, if you forget the transport, put the transport aside for a moment, the equation dTF equals collision operator is simply minimizing the entropy of F. And this collision, we know, this collision operator has a kernel which is comprised entirely of Maxwellians. So this Q of F is only zero if F is a Maxwellian. A Maxwellian, which is a Gaussian distribution in velocity, with with centered at the mean velocity, with the variance controlled by the temperature, and then with some coefficients in front to account for the density. So this is really the spatial density of the gas times the Gaussian mean velocity at the correct mean velocity with the correct variance, which is to say the correct temperature. And the property of this Maxwellian, you can characterize it by saying, take all the distributions F with the same moments, the same density, velocity, and temperature, and the one which minimizes the entropy is the Maxwellian. So this really is the minimizer of the entropy. And of course, that's roughly what the dynamics are doing. What this dTF equals Q of F is doing is taking F and relaxing it towards the Maxwellian distribution. So it's preserving the moments, but dissipating the entropy. Now, this dissipation gives you, give people an idea, which is, in fact, you can define a reduced model, this BGK model, where you replace the collision term with a relaxation term. You make this relaxation to the Maxwellian explicit, because at the end of the day, F goes to the Maxwellian. So you might as well say, okay, F goes to the Maxwellian. This is a simpler equation, and it's obviously not quite the same as the Boltzmann equation. It's not quite linear. It looks linear. It's not linear because, of course, the Maxwellian in question depends on the moments of F. So this dependency is not linear. But once you fix the moments, then this is just a linear term. So again, the equation is not really the same as Boltzmann, but it does have all the good properties. So you have, again, conservation of mass, conservation of momentum, conservation of energy, dissipation of the entropy, the equilibrium of the collision operator. The kernel of the collision operator is characterized by Maxwellians. And of course, by construction, this operator takes a distribution to the Maxwellian. So it's a very nice toy model in that it has all the macroscopic effects there somehow. And one can talk about how well this matches Boltzmann. In particular, this constant I have picked up in front of the collision operator, this mu, this collision rate. Technically, if you want to get a good agreement on the relaxation rates when you compare with Boltzmann, this thing has to at least depend on the density. This mu, this term appears when you derive BGK from Boltzmann, which you do by assuming the distribution F is close to Maxwellian. So you go to your collision operator, you assume the post-collisional distribution is Maxwellian, you simplify things, and you end up with this Maxwellian minus F plus a big integral in front, and this integral is what we are calling mu. But this integral does depend on f. So we are making an assumption here that this mu is just a constant, and this does reduce the complexity of the equation a lot, but it does give you non-physical relaxation rates. But in principle, you could make this depend on the density or the distribution, and anything that I'm going to say today will apply as well. Now, I do want to talk about kinetic mixtures. So in fact, all I've said was about a single gas, but in fact, I want a mixture of gases. So I want many species. In fact, there's 2 species, but this would generalize. So each species will have its own distribution and a mass, which may be different. So not all the particles have to have the same mass. All the particles of each of these species do have the same mass, for simplicity. So I have as many masses as I have species. Again, the mass of each species is going to be conserved in collisions because 2 particles come in, 2 particles come out. But now you can have transfer of momentum and transfer of energy between the species. You conserve the momentum in a collision, but if you have particles of different gases coming in and they come out with different velocities, there has been a net change of momentum, a net transfer of momentum from one species to the other. So it's no longer true that the momentum and the energy of Fp are conserved, but it's true that the sum of all of those momenta and those energies, that is conserved. And of course, one would really like a multi-species H theorem. One would really like an entropy dissipation result, because that way we can still think of this as this relaxation dynamics. We can still make this intuitions. So turns out, in fact, writing the equation for a kinetic mixture is not such a hard task, because the equation generalizes well. You keep one equation per species with transport and collision operator. And now the question is, how do you define this collision operator? One of the sensible ways of defining it is by defining it as a sum of the collision operator of the species you're looking at against every other species. So really you have a reprise of the same collision operator between species 1 and 2, 1 and 3, 1 and 1 indeed, because the gas collides with itself. And the total sum is the overall collision operator. And in fact, this is a sensible choice, because this boson operator that we saw earlier, this really lends itself to a multi-species generalization, because there is always a distribution of the velocity v, which you're considering, and the distribution of the velocity v star, which is the gas you're colliding with. So it's very sensible to just change f of v star by g of v star, and now this g is your second species. So this operator generalizes very well. This, I'm telling you, this is very old news. People have been doing this for 50 years. So it's not necessarily news, but it's interesting to know. And in fact, that this multi-species Boltzmann equation does have an H theorem. What's not so trivial is doing BGK, this replacing the collision operator with a relaxation to a Maxwellian and retaining the H theorem. Because of course, it's already not clear where you do BGK. Do you replace this collision operator, or do you replace each of these collision operators? And people have published both. There is a famous model by Bertram and some other people who I'm afraid I'm forgetting right now, where they replace this collision operator. So they say every gas is relaxing to the same Maxwellian with a temperature and velocity that come non-linearly from the moments of all these distributions. And that model, if I recall correctly, does not have an H theorem, or at least they didn't show that it did have an H theorem. So the paper I'm following today, at least the model I'm following today, is by Hag, Hawk, and Murillo, 2017. So you see this is relatively recent. The idea is to replace these collision operators here by BGK type collision operators. So for every operator PQ, you define a Maxwellian. So between 2 species, there will be a relaxation velocity and a relaxation temperature, which will give you 2 Maxwellians, 1 for each species. So the species number 1 is relaxing to different Maxwellians at the same time, 1 for species 1, 1 for species 2, 1 for species 3. And of course, in the long term, if everything relaxes, all of these Maxwellians become the same. But in the interim, they don't necessarily relax to the same one. And this is enough, in fact, to show an H theorem. So you do have an H theorem. So this intuition of relaxation to the Maxwellian does apply with many caveats. Now, I promised hydrodynamic limit. So, sorry. Well, I'll tell you first about the scaling, and then I'll tell you about the numerical method, sorry. So here's an innocent question. And innocent questions are the worst questions to ask in mathematics because they always have devilish answers. What happens when you take the Knudsen number to 0? What happens if the frequency of collisions is increased to infinity? Well, the intuition, again, I'm not proving anything, is that all Q is doing is taking you to the Maxwellian. All Q does is relax you to equilibrium. It doesn't change your moment. It preserves the density, the velocity, and the temperature. So when this term is infinitely strong, what should happen is that the distribution becomes Maxwellian really quickly. So that the solution to this problem is a distribution which is always Maxwellian, absolutely everywhere. And then the only thing that can change are the moments of that Maxwellian. So somehow the problem reduces, and you just have to determine what these moments n, v, and t are in space. Somehow the velocity dimensions all collapse. And in fact, you can show this. Fairly easily if you do the right expansion, or formally, of course. But it's not hard to take the right expansion on F and derive the compressible Euler equations from this. This is on the book of Sarzegnani. A lot of people in the room will have done this computation at some point. It's a nice computation, and it's very reassuring to see that indeed, when you take this limit, somehow, in some sense, you recover hydrodynamics. But this is very interesting because it means, okay, numerically, if we were to simulate this equation with a very small Knudsen number, 10 to the minus 5, which is the biggest Knudsen number I'll show you today, 10 to the minus 6, 10 to the minus 7, we should really see this behavior. We should really see the behavior of F to be just F is a Maxwellian and the moments satisfy the Euler equations. And this is good news in the sense that we understand the Euler equations fairly well. We have a few nice test cases. So we should be able to test this numerical method very well. The problem with this is, of course, okay, let's do the numerics, right? Let's try to put the very small epsilon and write a numerical scheme. So you discretize in time very valiantly. You arrive at your semi-discrete problem, and you realize your right-hand side has two terms with hugely different scales. You have the transport term, which has size 1, order 1, but then you have your collision operator, which has size 1 over epsilon, and this 1 over epsilon, again, this could be 10 to the 5, 10 to the 6, 10 to the 7. So I need a delta t of size epsilon if I do a naive explicit scheme. And this is bad news because 10 to the minus 5 is a very small delta t, especially if you're having to compute this collision operator on every iteration. So this numerical scheme suddenly becomes a lot of work. Could you do an implicit scheme? I guess you could. I haven't tried, but again, this collision term is fully non-local, so you're going to get a problem in many dimensions with a full Jacobian. This is bad news for an implicit scheme. So it could be done, yes, but I'm sure it'd be very slow as well. So we would really like an explicit scheme where we can have some kind of asymptotic preserving property. We can solve this problem and not die of old age in the process. Then again, this problem does have the right structure because, sorry, was that a question?
No.
No, okay, sorry. This problem does have the right structure because, again, this fast dynamics, this really strong collision operator, is really just doing the boring part of relaxing you to the Maxwellians. So somehow the solution space looks a bit like this. There is a nice, interesting curve in the middle of the space, this family of Maxwellians, and the dynamics happen there. And if you happen to start away from that curve, Q just sandwiches you to this curve very fast. So the dynamic where you converge to the Maxwellians is very fast, and then the evolution on this manifold is very slow. And the slow evolution, which would be the evolution of the moments, that's the one we care about. We don't care so much about the relaxation. So, perhaps there's some hope. Indeed, these ideas of projective integration that I mentioned are exactly the right thing here. The intuition, I think, is very simple. The idea is you start your simulation wherever you are. You take some very small time steps of size epsilon. So you pick your favorite numerical scheme for kinetic equations. Say you do forward-Euler for simplicity. You discretize your collision operator as best you can. You take a few small steps. You arrive at this family of Maxwellians, and now you're in the right curve. Now you're in the right place. So once you take a couple of steps into that curve, once you are firmly on this manifold, you take 2 points and you take an extrapolation forward. You take a big projection ahead of you of size 1, so something not of size epsilon, something of size 1. And of course, when you take that projection, you immediately leave this good manifold. You've immediately left the Maxwellian distribution. And if you were to do this again, if you continue to take large steps, you would blow up. This would not be stable. So what you do is you go back to doing small steps. So you do a few small steps and then a large step, a few small steps and then a large step, a few small steps and then a large step. And my hope is, if you get the right size of the projection and the right number of small steps, you can play this game of getting close to the surface, extrapolating away, getting close to the surface, and extrapolating away. This is obviously quite delicate. If you just pick any parameters, there's no guarantee that they should become stable or they should be meaningful in any way. So I have to justify this to you. But it does, in fact, work rather well. So here's a description of the method. This slide is my least favorite slide in the whole talk. It's not so important how we do it. This is just to say we do have the parameters are what's interesting here. We have the 2 steps. We pick a small step and a big step, and these are fixed. So I will pick them at the beginning and fix them through the simulation. The small step is really of size epsilon. It's epsilon or epsilon over 2, something just really small. The big step is size 1. And I decide how many inner steps I will take. And then you do exactly what I've described. You start with your Fn as this Fn0. You do a sequence of k+1 steps of forward-Euler with any old spatial discretization. This doesn't matter so much. And when you have your Fnk and Fnk+1, these are 2 points which are firmly on the Maxwellian manifold, you then do an extrapolation. You use Fnk+1 and nk to approximate the time derivative of f. This is the total time derivative. And then you do forward-Euler. You say, well, the next point is the previous point plus the derivative times some delta t. So it's almost, it's almost too simple. When the first time I saw this, I thought this cannot possibly work. And in fact, it does. It has been used. It was first introduced in 2003 for differential equations, for ordinary differential equations. Has been used in a range of problems, and it works surprisingly well. Why does it work surprisingly well? It's a good question, and the answer is you need to have some information about the spectrum of your problem. But we happen to have a problem with a very clean gap on the spectrum. We have really 2 clusters of eigenvalues, a cluster very close to the origin, which are the transport modes, roughly speaking, and a cluster of size 1 over epsilon, which are the fast modes, the modes, the relaxation modes corresponding to the collision operator, roughly. And there's a clean gap in the middle. So in fact, you can do a very similar stability analysis as you would do with a forward-Euler scheme and show that you can make the scheme stable. For forward-Euler, the usual thing that we teach undergraduates is to pick the delta t. So you shrink the spectrum into a stability region. You know that the scheme has a stability region, which is a disk of radius 1 centered at -1, 0. So you take the spectrum of your problem and you pick delta t small enough such that this spectrum fits inside this stability region. But we do the same thing here, really the same thing. It's just that the stability region is a bit more complicated. But in fact, you can show, this is shown in one of these Kieran Kivakaitis papers, and it's not difficult to do the computation yourself. But in fact, there is an asymptotic stability region. This is asymptotic when delta t0 is quite smaller than delta t1. But if you go to a limit where delta t0 goes to 0 and delta t1 is constant, this is the asymptotic stability region, which depends on this m, this relative size of the extrapolation. And this is a very clean 2-disk structure. So you take your 2-cluster spectrum, pick delta t0, delta t1, and k, so that the spectrum fits inside the stability region. And then you're very happy because this method is at least stable. Now, usually I don't go into so many technicalities here, but I think it's interesting to discuss what really happens at this level. Because of course, you may not have just two clusters, you may have more clusters. In fact, as soon as you have two species in this system, you have now transport and collisions. But if you have two species, you immediately get an extra cluster in the middle. So now you have three clumps of eigenvalues. But this is fine. This is not bad because you can do projective integration on projective integration. So you can use the projective integration scheme as the inner scheme of a projective integration method, you see? So now you do very small steps to capture the really fast modes. You do a projection step of size the order of the medium modes, which is stable by the previous analysis. And now you use this as the inner step of a projective step for the slow modes. So somehow you do half of the collision modes, then the other half of the collision modes, and then the outer layer gives you the transport. So again, the stability analysis can be done for a many layer scheme. So asymptotically, you get this many disk structure. And well, now there's a few technicalities here. There's more interesting things you can do. So for instance, why is really the scheme, why is it true that the spectrum is really three clusters? And the answer is because we took this collision rate in front of the BGK, we took it as a constant. So if you take it as something which depends on the density, then that spreads your eigenvalues around, and in fact, you can have a case where you have eigenvalues in the entire negative real line from this point all the way to the origin. So this scheme consisting of disks is no longer good enough. But this is the asymptotic stability region. In fact, if you pick middle steps, which are not too small, these disks actually merge. So there are configurations for the scheme where you get a single stability region, which looks a bit like, like one of those ice lollipops where there's like three balls, but they sort of merge in the middle. So in fact, they contain the entire real axis from some minus constant all the way to 0. So having more species would introduce more clusters. You'd have to do more levels. Having this dependence on the density would introduce a more complicated structure, but you can still capture it by picking the right levels and the right parameters. So it turns out to be a very versatile problem. In fact, if you did this spectrum and the simulations I'll show you are multi-species BGK. If you did Boltzmann, this is as good as taking the collision operator and making it depending on the density. So you would also have to contain the entire real axis. But the point is you can always perform this kind of stability analysis. And usually you can find parameters which are well behaved. So I'll give you some examples just to show that the numerics in fact work and we can pick sensible parameters. The first thing I'm showing you here is the usual test case for the Euler equation. If you've ever done hydrodynamics, you've solved the sub tube. This is an initial condition, which is a discontinuity in the density. And the velocity and the temperature. And this is an interesting problem because it gives you the whole range of phenomena you can get in a hyperbolic equation. You get a traveling shock on the right, you get the rarefaction wave on the left, and you get the contact discontinuity in the middle. So if you write a hyperbolic solver, this is the first problem you solve. But of course, the dynamics of our multi-species BGK should asymptote to the dynamics of Euler. So we should be able to solve the subtube problem. And in fact, what we're solving here is a mixture subtube. So instead of having a discontinuity in one species, we simply take two species, one on each side of the discontinuity. So you start with the two densities separated by the discontinuity with the right quantities. You can perform the analysis for a mixture very much like you perform the analysis for a single gas. And then you look at the solution. So this is the total density of the mixture. And in fact, the solution to this subtube is that the two gases remain separated by the contact discontinuity. So there's no mixing in this example, and you can check this numerically. And what we see on the left is exactly what we expect. Here I'm plotting the total density of this numerical solution. The dashed line is the analytical solution of the subtube, and you can see that as I take the Knudsen number to 0, the solution really does converge to that. So for a Knudsen number of 10 to the minus 1, the solution is just a single smooth curve. You can't see anything. For 10 to the minus 2, you start to see this very characteristic step structure. And then for 10 to the minus 6, you really are quite close to this subtube structure, which is reassuring. We are recovering the hydrodynamic structure from the kinetic equation. And of course, if you did this naively, you would need delta t 10 to the minus 6. And of course, this is not what we did. On the right, perhaps more interestingly, I'm showing you the same simulation for the Knudsen number 10 to the minus 6, but now I'm showing you different mass ratios. So on the left, the mass ratio was 1. Both gases have the same mass. And because of this, it's the same as solving the one gas problem, because these two gases are indistinguishable now, because they're ideal gases and all the particles have the same mass. On the right, we introduce a mass ratio. And in fact, we introduce quite a high mass ratio. We'd start with a mass ratio of 5 in the red curve, but then we go to 30, and then we go to 100. And this I haven't seen in the literature, because this introduces another type of stiffness to the problem. When you go to a mass ratio of 100, again, you have momentum conservation when you have collisions. But if you conserve the momentum in a collision and one of the particles is 100 times heavier than the other, the velocities you reach with the light particle can be quite high. So this is yet another challenge in this numerics. And what's quite nice is that overall the behavior of the solution is as good. So increasing the mass ratio doesn't make the simulation any worse. With the notable exception of the interface, you see around the contact discontinuity, where the two gases are meeting, when you have a heavy gas, the heavy gas really does like to push the light gas a little bit. So there is this extra ripple, which we don't see with a mass ratio of 5 or a mass ratio of 1, which seems to be a consequence of the mass ratio, but it does go to 0 as you refine the Knudsen number. So the convergence is still there, but it does have some new characteristics which you don't see on a one gas simulation. And again, this one legitimate question you can ask is, what happens to the parameters of the model, of the scheme, I mean, when you take the mass ratio to 100, right? Do you now have to take 20 times the number of inner steps? Do you have to take the delta t's much smaller? And the answer is no. The answer is these simulations, we do them as follows. We will pick where are my parameters? We will pick the same delta t and delta t1, or in this case, delta t2 as well, because there's 3 levels. So the delta t's will be fixed, and the only thing that changes when you increase the mass ratio is the k, so it's the number of inner steps. And this number of inner steps grows logarithmically on the mass ratio. So when we went from mass ratio 1 to mass ratio 100, k went from 4 to 6. So yes, it's higher. This is not an asymptotic preserving scheme in the classical sense, but it is a very well-behaved scheme. When you make the problem a lot more singular, you barely have to change anything, and you can still capture the behavior quite well. So we were very pleased with this. Something a bit more interesting. This is a Kelvin-Helmholtz instability. This is a very classical fluid dynamics problem where you have 2 streams, 2 fluids flowing past each other, one above the other. And when you introduce is a little perturbation of the interface. Here is just a sine wave with a very small amplitude. And what happens is, very promptly, this little imperfection in the boundary generates vortices. And for a period, these vortices grow exponentially fast. So they appear very quickly, and then they start to mix, and they break down. And here we have a simulation with a Knudsen number of 10 to the minus 5. We had to use a fine grid in position and space, position and velocity to capture it. So the total discretization uses 16 million cells, which is a fair amount of cells. And using the telescopic method here decreases the cost by a factor of 5. So doing your simulation 5 times faster it's nothing to scoff at. And indeed, you can see that the simulation is quite neat. I quite like this one. Something else with Maya Meshkov. This is a different type of instability. This one is perhaps harder to explain, but what you have is you have two gases, a light gas and a heavy gas. So a mass ratio, I think it's 5 in here. And at the interface, you have this kind of curve, and you have a hyperbolic shock traveling on the light gas. So this hyperbolic shock travels on the light gas, arrives at the interface, hits the heavy gas, and when it hits the heavy gas, you get this jet of heavy gas injected into the light gas, and you get this characteristic mushroom cloud structure around it. And again, 81 million cells in position and velocity, because otherwise we wouldn't see, if you want to see these vortices, you really need enough resolution. The Knudsen number here was 10 to the minus 6. So again, quite a costly simulation had we just done forward-Euler. And here the factor of improvement is 9. So this simulation is almost 10 times faster to compute using telescopic projective integration than if you just use a forward-Euler method, say. And then to conclude, this was perhaps my favorite. It's the silliest one, but I really like it. It's a shock bubble interaction. So you have on the left a light gas, which is just a hyperbolic shock configuration. And then on the right, you have a bubble of a gas. So it's an exponential bubble. So the density of the right gas is 0 really quickly outside of an area. And then you have this little exponential bubble. And what happens is the shock hits the bubble and drags the bubble along. You can see the bubble is being taken to the right and deformed. And also you can see that the shock slows down. There is some ripples on the light gas after the interaction with the bubble. It's really quite a nice, I really like this one. It's really quite a nice simulation. And again, this one here, we went a bit crazy, just 200 million cells. So, really, if you want to see the resolution, you really need the cells. The Knudsen number here is 10 to the minus 5. And because of the integration parameters, here the telescopic projective method decreased the cost by a factor of 18. If you're solving a kinetic equation with 200 million cells, having your simulation 20 times faster is really something significant. Here is the same plot, but on 3D, in 3D, and just so you can see how the bubble is squeezed and then dragged along. So yes, I've told you a little bit about everything, I think. Just to conclude, we have this method. You can tune the parameters to capture this stiff problems, which would be hard to simulate with a numerical scheme. This method generalizes well, so you can start with a 2-level method, but it generalizes to many levels. It generalizes to complex dependencies of the collision rate. The improvement factor depends on the eigenvalues of the problem, depends on a number of things, but it's consistently above 5. So all the examples I showed before today were 5. I didn't tell you here, on the paper, we actually write a real-time CPU comparison of the sawtooth problem, not just a theoretical improvement in terms of number of operations. And the improvement on the sawtooth was a factor of 10 for epsilon 10 to the minus 5, but then it was a factor of 100 for epsilon 10 to the minus 6 and 1,000 for 10 to the minus 7. So as you decrease the Knudsen number, the complexity of the projective method really does not increase, whereas the complexity of the direct method would, of course, increase. So it really seems to provide a nice shortcut to solve these equations. Seems to not affect the quality of the simulations because we can still capture all the hydrodynamic behavior. And it seems to generalize quite well. We did multi-species BGK. Thomas before had done a single species Boltzmann. We're currently doing this for the Landau equation, and we have some early results. So I think it's a nice scheme. So hopefully I sold you on the numerical scheme. Thank you very much for listening, and I'll be happy to take any questions.
Thank you, Rafa, for the great talk. Any questions? Yes.
Yeah, but very nice talk. Also heard extremely nice movies. How do you find that this compares to sort of IMEX schemes to handle this stiff collision operator? Would you say that your explicit treatment is able to handle a wider variety of collision operators, or where would you say that?
So when you say an IMAX scheme, you mean making the collision operator implicit?
Yes.
So I haven't done a direct comparison with this. Obviously, an implicit scheme has huge advantages. So if you were to say that the implicit scheme can capture the behavior of the solution better, I would be inclined to believe you. However, the great advantage of this method is the simplicity. Is that it's completely explicit, right? If you want to solve an implicit scheme for a kinetic equation, this is a tall order, numerically speaking. I'm sure the schemes are very good. In fact, I thought about them myself. I'm sure you can do interesting things. But of course, an implicit scheme, in terms of how hard it is to implement and also how hard it is to then run, every time you run the solution, this is much slower. So, of course, at the end of the day, it depends about what you care. Do you care about fast simulations, or do you care about high accuracy, or do you care about a compromise? So I'm not saying this is the one method that you should always use. I'm saying this is a fast method which gets you where you want to go very quickly. There may, of course, be better methods. This I cannot argue with.
So, Rafa, I have a question. So, for this multi-species model, do you have any result for separation? Any
analytical result?
For the spectrum of this multi-species?
No. The analytic treatment of the spectrum of these equations is very lacking in the literature because it's hard. There's, for Boltzmann, there is Ellis and Pinsky, but this is from the 70s. Pierre de Gonde and Lemieux did the spectrum of Landau, and then there is some results here and there, but there isn't, I'm not aware at least of a definitive word on the spectrum of multi-species Boltzmann. However, numerically, what we did is we approximated the spectrum numerically to then fit the parameters of our scheme. And numerically, this is always what we observe. We observe very clean separation of the modes.
And that separation, based on your numerical result, that separation really depends on the mass ratio.
Yes. So, in fact, when you make this collision rate depend on the density, or if you increase the mass ratio, then the separation becomes less clear, which is why you need to change your parameters a little bit. In the case of the mass ratio, the separation survives, but it just becomes less pronounced. Whereas in the case of making your collision rate depend on the density, then the separation disappears completely, and you really need a method where all the stability regions merge.
Okay. I think we have a question from the audience.
Rafa, I have a question. Just a follow-up on Jean Wei's question. Can you, has anybody computed numerically the eigenvalues to have an idea?
No, we computed numerically the eigenvalues. We cheated, in fact, because we used one-dimensional computations to approximate the parameters for the 2D, 2V problems. Yeah. Because, of course, computing the eigenvalues of this guy is a whole... It's a whole paper on itself, right?
Yes, right. That's why I was asking. If
No. This is, I mean, you can do it because you have your matrix and you can diagonalize this. But of course, numerically, unless you do something clever, this becomes very expensive very quickly. And we didn't do anything clever for this. We computed, and there is some, if you look at the papers of, again, if you look at the paper of Boltzmann and Landau, there is reasons to believe that the spectrum does not depend too badly on the number of dimensions. So if you have an estimate for 1D, your estimate in 2D should not be too different. So in that way, we really cut a lot of time by just doing 1D spectra and then estimating. But there is no theory supporting this that I know of.
Yes. Okay. Well, more work to do.
So regarding the spectrum of multi-species Boltzmann in the linear setting, there is a paper in 2016 by Esther Dawes, Clément Moupeau, André Hugel, Nicola Zamponi, and they use some coercivity estimates on the multi-species.
Yes, you're absolutely right. In fact, I believe we cited this paper on our work. I forget. There was a reason why this result wasn't completely general. I'm afraid I forget if it was. I forget if they use a perturbative regime, but that wouldn't be a problem for us because we are always close to the Maxwellian. So maybe they do. I seem to remember we discussed this paper at some point. We concluded that the estimates were not what we needed. I'm afraid I forget why this was the reason, but it should be written down. We've definitely cited these people because this is true. They do have a result. I'm afraid I cannot remember why we didn't use this paper. I'm sorry.
Other questions or comments? If not, let's thank the speaker again.
Thank you very much.
I'm going to run for the cake.
Yeah.
All right.
Recording after the conference.
Keep a piece for me too, please.
Yeah.
Oh, yes.